Okay, energy mass reactions or equivalence in nuclear reactions. Just like in a chemical reaction, where some chemical combinations are more stable than other chemical combinations, in nuclear physics, some nuclear arrangements are more stable than other nuclear arrangements. And so what we assume is happening in a nuclear reaction is that mass is being converted directly into energy, but it's unclear why that's happening. At first, you might assume that when fusion occurs at the sun, that actual protons and neutrons are disappearing, and that the disappearance of those protons and neutrons is what results in the massive amounts of energy that we observe. But it's not true. What is actually happening is that protons and neutrons are not destroyed, but instead that they exhibit a different mass when they are in different nuclear arrangements. What I mean by that is that a proton does not exhibit the same mass regardless of its state. If a proton is in a hydrogen atom, it exhibits a specific mass. If that same proton is fused with other atoms until, say, it's in a carbon atom, then it will actually exhibit less mass than it did when it was in the hydrogen atom. The reduction of that mass is what is the mass that's available to be converted into energy according to Einstein's famous equation, E equals mc squared. So protons and neutrons themselves are not disappearing unless it's like a matter-antimatter reaction. But in normal nuclear reactions, what's happening is that the mass of a proton is actually changing when it goes from one state to another state. Specifically, if we look at the atomic number of the element that the proton is included in, what we would find is that there's some arrangement that looks like this. This is the mass of the proton. The proton's mass, and I'll do it in relative atomic mass units. So we might remember from chemistry class that carbon-12 was used as the benchmark. So one atomic relative mass unit in carbon-12 is exactly 1. What we find is if we go down to elements like hydrogen, the mass of that proton is a little bit higher. In fact, it dips until it reaches a minimum, and then it actually comes back up a little bit. This minimum occurs at iron 56. And in that general region, that first row of the transition metals. That's why large planet or rocky planets like Earth have iron cores, because in stars, the mass of protons is going to try to seek the lowest point. And so as fusion processes happen, small atoms are built together to form larger atoms, and the reduction of the proton mass leads to enormous amounts of energy being released. Alternatively, in fission reactions, very large atoms are split apart, still heading towards this minimum in mass that occurs somewhere around iron 56. What that means then is that just like all other systems, the system tends toward the point of the lowest energy, and so all elements are tending towards iron 56 or those middle range transition metals. So fusion occurring in stars bulks them up, and then fission that will occur naturally to some extent, but that we largely use in power plants, will break them back down so that they both head towards that minimum amount. If we know the exact mass of all the neutrons and protons that occur in a specific atom, and we have to know what atom it is because I just said that they have different masses depending on what type of element they're contained in, then what we can do is we can figure out exactly how much of that mass is available to be converted into energy when the reaction occurs. If we want to use the E equals mc squared equation, this mass probably should have been written as delta m, where we recognize that delta m is going to be the change in mass where the of the products minus the mass of the reactants. Or how much less mass do I have now than I had before? In fact, it should be negative this delta m, because whatever the reduction is here, that's how much mass is going to be available for the reaction. One of the common nuclear reactions that would happen in the sun, or one of the nuclear reactions that we would be exploring to try and use nuclear fusion, is the fusion reaction between deuterium and tritium. Specifically, a deuteron and a triton, not deuterium and tritium, that's those things in water. Anyways, a deuteron and a triton. Those are both isotopes of hydrogen. A deuteron is a hydrogen atom that has a neutron, and a triton is a hydrogen atom that has two neutrons. So those could also be thought of as hydrogen 2 and hydrogen 3, although they get special names. When those two things are fused together, they produce an alpha particle, helium, and a neutron. Looking at this example, we can compare the mass of the products to the mass of the reactants to figure out exactly how much mass is available for energy. These values are all given in relative atomic mass units, and so we'll also need to know what one relative atomic mass unit is worth so that we can convert to kilograms and use Einstein's equation. So the mass of the products minus the mass of the reactants will give me my change in mass. My products here are my helium, so my 4.00151 U, and a neutron, 1.008 U. My reactants are the deuteron, 2.0141 U, and the triton, 3.01605 U. On first inspection, we can see that those two numbers are very close together, but they're not all exactly the same, so let's find out the exact change here. Excuse me. So this is just calculator work. I just punch all that in, and I'm getting a change here of 0.02064 U, negative, representing that that's how much less mass there are in the products than the reactants. Using my value for U, I can figure out what that exactly is in kilograms. I got 3.43 times 10 to the negative 29 kilograms. Again, negative, that's a reduction. And since that is being made available to energy in E equals mc squared, that's going to work out to 3.087 times 10 to the negative 12 joules of energy. That doesn't seem like very much energy, but if we consider the fact that that's from one atomic process, that's an enormous amount of energy. Usually when we think about energies, we're thinking about the energies that result from a whole bunch of atoms, tons and tons of atoms reacting. So when we come up with this energy for just one process, it is a huge amount of energy. Again, one more thing here to notice. Here I had 4 plus 1 protons and neutrons, or 5 particles. Here I had 2 plus 3, 5 particles. Notice from that the overall number of particles doesn't actually reduce. right? 5 particles go to 5 particles. It's that the particles exhibit different masses in the different states that leads to us having a reduction in mass that can be converted into energy.